Today I will talk about the valence bond theory, and if you remember from my previous video, I talked about the Lewis theory and the VSEPR theory. And Lewis theory of chemical bonding does not clearly explain why chemical bonds exist, and VSEPR is used to predict geometry of the molecule. And for instance, if we look at the Lewis theory, we can give two examples. One of them hydrogen and the other is hydrogen fluoride. And if you look at their Lewis structures, we have one electron for hydrogen for each hydrogen, and we make bond in Lewis theory. And in hydrogen fluoride example, we can make the bonds between the hydrogen and fluoride by sharing again these electrons. The issue is that according to the Lewis theory, there is no difference between them. But in reality, bond enthalpies of these molecules are very different from each other. For instance, for hydrogen, it is 436 kilojoule per mole, and for hydrogen fluoride, it is 150 kilojoule per mole. So they are very different from each other. The issue is that Lewis theory does not explain the bond formation chemically. So we need another theory to explain the bond, why these two bonds are very different from each other. So we have chemical bond formation, and Lewis structure cannot explain it. So to understand the chemical bond formation, basically we need quantum mechanical approach. We have two theories. So one of them is molecular orbital theory, or basically MO theory. The other is, so today's topic is Valence Bond Theory, or VB theory. Both theories depends on the quantum mechanical approach, and today I will talk about the valence bond theory. So simply, valence bond theory states that a stable molecules form from reacting atoms when the potential energy of the system has decreased to minimum. And the valence bond theory can explain the covalent bond formation, and this covalent bond formation is due to the hybridization of the atomic orbitals. We create the atomic orbitals to make the bonds between the atoms. And I want to give an example to explain the phenomena. We can think hydrogen again. As you know, we have one electron for the hydrogen, right? We can write this kind of structure for the hydrogen for electron configuration, and we have another one electron for the second hydrogen. And these electrons are in the 1s orbital. What is the 1s orbital? 1s orbital is something like this in the XYZ space. So it's a perfect sphere, and the electrons can occur in this sphere. So this is the most probable place to occur for the electrons for the hydrogen. So this is the 1s orbital. And if we draw the potential energy versus distance, hydrogen molecules, so each hydrogen atom combines, right? But the issue is that we have an proton here, right? We have another proton here. So two plus charges repel each other. Another problem is that also electrons, we have one electron here for this hydrogen, and we have another electron for the other hydrogen, and they can also repel each other if they are too close to each other. So as the atoms approach each other, each electron is attracted by the nucleus of the other atom, and at the same time electrons repel each other. While the atoms still separated, attraction is stronger than the repulsion, so that the potential energy of the system decreases. So we have a potential energy, okay, and it decreases some point. And if we separate it, potential energy between them becomes zero at the infinity. So at the infinity, potential becomes zero. So this is the zero level. So molecules here, so the hydrogen molecule or the hydrogen atom has the smallest or the most stable formation. So there's a bond between them at some distance. So this is the distance. And if they're separated, distance increases, and then at the infinity they're separated and there will be no attraction between them. So this is the idea. So this condition corresponds to substantial overlap of valence orbital and the formation of a stable hydrogen molecule. So this is the stable hydrogen molecule formation. And what happens is that for the valence bond theory, we have one s orbital for hydrogen and we have another one s orbital for the hydrogen, and hybridization occurs and electrons distributed well among the two hydrogen atoms and makes a bond. This is the idea of the valence bond theory. And we can continue to more complicated molecules, for instance CH4 or the methane. As you know, we have carbon with 6 electrons. So if we write the electron configuration or the carbon, we have something like this, right? And I want to write the electron configuration in a simply an MO diagram. Not MO diagram, but the energy versus the orbitals. Okay, energy increases from bottom to top, and at the bottom we have the 1s orbital, and we have 2 electrons for the 1s orbital. For the second shell, which is the 2s, we have again 2 electrons, and we have 2px, 2py, and 2pz orbitals, and we have 2 electrons for each one. However, we want to make 4 bonds for the methane molecule, and we need hybridization. Since valence bond theory depends on the hybridization, we have to create 4 hybrid orbitals. Since the reason is that we have 4 bonds. 1s orbital energy is too low and it does not a piece of the hybridization process. But 2s and the 2p orbitals has close energy and they create hybrid orbitals, which is the 2sp3 orbitals, and we have 4 of them. So basically in CH4 molecule, carbon atom has 2sp3 hybridization state, and each of the orbital has 1 electron that comes from the carbon. On the other hand, we have a hydrogen 1s, right? We have a hydrogen, this is carbon, and this is the hydrogen, or just H. We have hydrogen here, and we have 4 of them. each of the hydrogen have the same energy state, and all the orbitals have one electron, and these electrons will occupy in the atomic orbitals, and these electrons go to the atomic orbital and makes the bond. If I want to draw the CH4 with the hybrid orbitals, I have a carbon atom, and this is one of the 2sp3 orbital. Okay, I just want to draw the one face. Actually, there is another face here, a small one, but to make it clear, I will not draw the small face. And we have 4 of them. So we have 1, okay, and we have hydrogens, and this is the hydrogen 1s. Carbon has sp3 hybridization, and each hydrogen has 1 electron, and these are the electrons for the hydrogen and for the carbon. If you look at this bond, this is a sigma bond. There is a beautiful overlap of the 1s of the hydrogen and the overlap of the 2sp3 hybrid orbital of the carbon, and it makes the beautiful bond. And as you know, the CH4 has tetrahedral geometry, and the angle between these two hydrogen is 109.5 degree. And we can make another example, which is ammonia. And if you look at the Lewis dot structure, we have 2 lone pairs and hydrogen atoms around the nitrogen. So what is the hybridization of the nitrogen? So we basically count the lone pair plus the bonds. So we have 1 lone pair and 3 bonds, and we need 4 hybrid orbitals, which means that we need to make sp3 hybridization for the nitrogen atom. So simply S is 1, P is 3, and it is equals to 4. This is the sp3 hybridization. Again, we can draw the nitrogen and hydrogen bond. This is the hybrid orbital, and this is the 1s orbital of the hydrogen, and they combine each other, overlap, and create a sigma bond. We can also show this sigma bond as nitrogen 2sp3 comma hydrogen 1s. These are important for the exams. But what about the double bond? What is happening for the double bond formation? So in this case, what is the hybridization of the carbon atom here? So double bonds occurs overlap of the p orbitals, but the overlap is not is not very good. What I want to say is that, so firstly we need to know the hybridization of this carbon. We will count the sigma bonds, and it is 3 for this carbon. I will just look at this part. We have sp2 hybridization for the carbon atom, and we can draw it. We have a carbon atom here, and we have another carbon atom. Again, hydrogen has valence orbital, another valence orbital, another valence orbital, and another valence orbital. But also we have pz orbitals for each carbon. So this two group closes each other, and between these two carbon atom we create a sigma bond. This is a sigma bond. And the pi bond occurs between these two pz orbitals. So the overlap is poor. There's a poor overlap between them, and we can draw it as something like this. Okay, there is a poor overlap. And these are the electrons for each carbon. And again we have electrons for the hydrogen and the carbon, and these are also sigma bonds. So we can write this pi bond as pi carbon to py, comma carbon to p, not phi, carbon to pz, and carbon to pz. And the sigma bond, this one, can be represented as carbon to sp2, comma hydrogen 1s. And this sigma bond is between carbon to sp2, comma carbon to sp2. And this is the valence bond theory. And due to this pi bond, these two carbon atoms does not rotate freely. And this is the explanation, and it is an exam question. Why these two carbon atoms doesn't rotate freely? The answer is very easy, since there is a pi bond, and pi bond prevents the rotation of these two carbon atoms. And thank you for your attention.